All right, so I have a relatively short lesson looking at introducing the idea of what a perpendicular bisector is. And really the point of this lesson is to prepare us for the next one. But in general, if I have any 2 points, I got 2 points A and B. If I imagine a line of, if I imagine points that are equidistant from A and B, which means a point that is the exact same distance as it is to A as it is to B, any of these points you see here, E, D, C, F, G, they are all the same distance from A to B. And if I kept going, this point up here, this point down here, all these points are the exact same distance from A to B. Connect the dots and you got a vertical line. And this vertical line is always perpendicular to the line that connects A and B. And it always runs through the midpoint of that line. And that's kind of what's described right here. I guess last thing I should say is that line I'm describing, that I'm drawing in red now, we call that a perpendicular bisector. That's the fancy word for it. That's the perpendicular bisector of A and B. It's the vertical line in which every single point on it is exactly equidistant from A to B, the same distance from A to B. And it always has these characteristics where it is perpendicular to the straight line distance between those 2 points, and it passes through the midpoint. All right, and as usual, the best way of understanding this is to just try using it. And so what I have here are 2 points, A and B, and I want to sketch the equation of the line in which all points are equidistant from those, which means everything I'm asking for here is the same as asking what is the perpendicular bisector of A and B. So let's visualize this. First thing I'd like to do is draw the line connecting A and B. The ruler apparently is not very straight. Anyways, this perpendicular bisector will always go through the middle of this. So that midpoint there, which I can just see by looking at this graph, is at 1, 2. Now in case that's my midpoint. Now keep in mind if I can't just see it or if the numbers aren't so pleasant, don't forget midpoint's a very easy calculation. It's just the average of your x coordinates, the average of your y coordinates. So I'll write that down right here as well. So the midpoint in this case would be, if I look at my x coordinates, -1 plus 3, divide by 2, and my y coordinates, 1 plus 3, divide by 2. I'm finding the average of those, or the mean, which brings me numerically to 1, 2, which I could see by looking at the graph. Again, though, don't assume you can always just, it could be nice whole numbers or whatnot. All right, so the perpendicular bisector will go through that point. It'll also be perpendicular to this line I drew in gray, that line that connects A and B. And we learned about how perpendicular slopes or gradients compare to one another. And so first let's find the gradient or the slope of AB, which I can just see the slope is 1/2. And so I'll say the slope or the gradient, I'll say slope because it's less letters. The slope of AB, remember, is rise over run. I'll write this down here, but I'll review. And so it's 1/2. So that's the slope of this line connecting A and B. Well, let me visualize this perpendicular bisector. It will be perpendicular to this, which means it'll be another line that crosses what I've highlighted in blue at 90 degrees. So I'm going to estimate it to look something like this. Oh, this is a terrible ruler. Why are you so mean to me? Oh, take 3. Oh, what is... I know you don't care, but I do. So I'm going to try again. What are you doing? Anyways, I guess that's good enough. And it crosses at 90 degrees like that. And so what really matters, though, to be more accurate, this is just a sketch. I can't put too much detail into my sketch, is to remember that that line I just drew is perpendicular to 1/2, and perpendicular lines have slopes that are opposite reciprocals of one another. So that means the slope of the line perpendicular to AB, the perpendicular bisector, will be the reciprocal of 1/2, which is 2/1, and the opposite sign. So 1/2 is positive, this will be negative, or just -2. And that's the slope of this perpendicular bisector. Which, keep in mind, that means from any given point, I go down to over 1, which I can actually see from what I drew. If I pick any point, go down to over 1, yeah, down to over 1, or up to backwards 1. Either way, Again, I can look at this visually or numerically. And so now if I want the equation of that line, remember to find the equation of any line, all you need is the point and a slope. Now I can actually see, because I have such nice numbers here, I can see the equation of this line. Has a y-intercept of 4 and the slope is -2, so I know one version of the equation would be -2x plus 4. Just again, don't assume you can always just see those things right away. So while I have that, what always works is if you know a single point and the slope or the gradient, you can use this point slope or point gradient formula, which we've seen before, you've learned before. So y minus y1 equals the gradient times x minus x1, where y1, x1 is just some point. And again, I know it goes through 1, 2, so I can say y minus 2, that's the y coordinate of that point, equals the gradient or the slope of that perpendicular line, x minus that 1. Keep in mind, y1, x1, I'm using the midpoint because I know it goes through there. And again, I can just confirm what I said before is correct. I get y minus 2 equals -2x plus 2. Add 2 to both sides, y equals -2x plus 4. I don't specify what form to write my equation in, but y equals -2x plus 4 is one of the more common ones. And so keep in mind, everything I did here, I actually could have figured out purely visually. I didn't really need to use any of these formulas. That's just because I had such nice numbers, and then my numerical work just kind of backs it up. And so again, that there, what I just drew, this line here, I've highlighted in green, that is our perpendicular bisector. Every single point on that line is equidistant from A and B. All right, a little bit trickier. I got 2 points here, A at -4, 4, -2. So there's A and B, right on the x-axis at -4, 0. All right, I want to find the point that is equidistant from both of those, but also on the line 2x plus 3y equals 9, which is that line in green. So first, let's try to visualize what's happening here. I want to imagine a point that is somewhere on this line here, but is also the exact same distance from A and B. So I know, just from a quick estimate, it must be somewhere around here. Because if I just look, that and that look pretty similar. Whereas a terrible guess would be like right here. I'm sure we realize that and that are not the same distance. All right, so that's just my rough idea of where this is. Okay, and I want to find the coordinates of that point. So let's put x comma y for now. That's what we're trying to figure out. Okay, how can we do this? Well, that point x comma y, if it is equidistant from A to B, it must be on the perpendicular bisector of A and B. So let's try to visualize and think about how we can find the perpendicular bisector of A and B. First thing, let's imagine a line that connects A and B, the straight line between them, like we did before. And let's find the midpoint, which I can visualize. It seems to be right there. That seems to be my midpoint. Just to double check, the midpoint should be the average of my x's, or halfway between -4 and 4, which is 0, and halfway between my y's, halfway between 0 and -2 is -1. So that is my midpoint. And it should be perpendicular to that line that connects A and B, which if I look at the line that connects A and B, so I'll say the slope of AB, or the gradient of, maybe I'll say gradient this time just to be fancy. It's good to be fancy sometimes. The gradient of AB, I can see is -1/4. Go down 1/4, which means the slope of the perpendicular line to A and B should be the opposite reciprocal of -1/4. So instead of being negative, it should be positive. Instead of being 1/4, so it should be 4/1, or just 4. Which means I can actually visualize this perpendicular bisector quite nicely. It should go through that point I've highlighted in blue. It should have a slope of 4, or 4/1, which means from that point, I can imagine another point going up 4/1. So like that. So a little bit more accurate now. There's my perpendicular bisector. So that point x comma y, not that it really matters, I know is actually more like right there. Okay. But again, how can I actually find that point with full, complete accuracy? Well, what I'm really now doing, if you notice this, is I'm finding the intersection between two lines. The line in green, which I gave you the equation of, 2x plus 3y equals 9, and the line in red, which is the perpendicular bisector of A and B. And so let's find the equation of that line in red, well, in which I already know the slope of it. The slope of it is 4, so all I need is a single point. And in this case, that point is that midpoint, which I can see the coordinates of again are 0, -1, which is not only a point, it's also the y-intercept, which means the equation of that line in red, I can immediately just see that perpendicular bisector must have an equation of y equals the slope, which is 4 times x, plus the y-intercept, which is -1. So there's the perpendicular bisector. And here's the equation we always had. So I can just find now where these two equations intersect, which I'm really solving a system. And so now at this point, I want to solve the system between this perpendicular bisector and that 2x plus 3y equals 9. We've learned how to do this algebraically. We've also learned that your GDC has applications built in to do this really quickly, which is probably the most time-efficient way of doing this. And so I want to use my simultaneous equation solver to do this as quickly as possible, which means I want to put them both in the same form. This equation here is already in the form that my calculator wants, so I'm just going to rearrange this to put in that form. Basically, I'm going to rearrange it so now it's 4x minus y equals 1. And now they're both in the same form, and now I can solve this system. So I want to solve the system of 4x minus y equals 1 and the 2x plus 3y equals 9. Keep in mind, this is a pretty nice system to solve algebraically as well. For example, if I multiply my first equation by 3, I can use elimination to cancel out the y's. Either way, I don't really care. The fastest is probably still to use your GDC. So I'm going to say solve any way you want. And you should really quickly get to x equaling 6/7 and y equaling 17/7, or the point 6/7 and 17/7. Considering the answer here, these are not whole numbers, and sevenths are kind of, they're definitely annoying to decimalize. I would highly recommend just using your simultaneous equation solver in your GDC. It is going to be faster. And again, that's the point of this course, that we can use technology to solve these sort of problems. All right, last one. I have 3 points, A, B, and C, and you can see those dashed orange lines are the perpendicular bisectors between all of them. For example, this line here is the perpendicular bisector between B and C. And this line here, looking at this, must be the perpendicular bisector between A and C. All right, with that said, 3 questions that are all kind of the same. Determine the region in which all enclosed points are closest to A. All right, so in this case, I need to find all the points that are closest to A. So if I look between A and B, it has to be, here's my perpendicular bisector for A and B. So it's got to be everything on this side of that. But some of that stuff I highlighted is actually significantly closer to C. For example, everything around here, I can just tell by looking at it, is closer to C than A. So everything I've highlighted so far is closer to A than B, but there's still that point C down there. So while I'll keep that for a second, I also need to realize, let's do the same idea for A and B. Here's the perpendicular bisector of between A and C. And in this case, everything here is closest to A. But obviously some of that's closest to B. So in the end, what's the region I want to keep? It's kind of what I've highlighted twice. It's this region, which I'll clean up in a moment. I know it's horribly messy. This region right here, everything there is closest to A. Which, notice, if I now just clean this up and make it kind of nice and neat, still has boundaries of these perpendicular bisectors. But everything in this region here is closest to A. And then the same idea for the others. Determine all the enclosed area where all the points are closest to B. It's going to be the same idea, but it's going to look more like this, but with this boundary between B and C down here. And then likewise C, here we go, this region down here. So everything you see in yellow is closest to A, everything you see in blue is closest to B, everything you see in green is closest to C. Now, while I am actually done the question, a few things I would do. I also want to make these borders between them a little more clear. So in the end, the only borders that matter are this, and this. Those are the boundaries between these. And this point right in the middle, in this case, -2, 0, that is the point equidistant to all three. It is exactly equidistant to A, B, and C. Now this here, what I've just created, this is actually called a Voronoi diagram, which is what the next couple lessons are about. A Voronoi diagram is a visual that shows you all the regions which are, closest to any particular point. In this case, like I said, everything highlighted in green is closer to C than any other point. Anything on these lines that I've drawn darker are equidistant. For example, this point here is the exact same distance from A to C. And this point here, I'll draw up here, is the exact same distance from A to B. Whereas again, that point in the middle is equidistant to A, B, and C. So this idea of a Voronoi diagram is really what we'll start looking into, and it's really the purpose behind understanding what a perpendicular bisector is. But that's for another day.